So the next speaker is Professor Ayid Ghani from Carnegie Mellon University. He's going to speak on do we need to sacrifice accuracy to make ML models fair?
Thank you. I'm going to talk about two things, not for hopefully too long. One is really a teaser, which is, we all know that during COVID, all of us became epi people. We learned models and those lines, they always go up, they maybe stabilize, they never come down, all that stuff. What also happened in parallel is governments, for one, started thinking about using data to make decisions, not just justify decisions, but actually trying to make decisions. But they kind of went wrong in a bunch of places, especially around equity issues. So one of the things that happened was pretty much every government agency scrambled around COVID time to figure out who do we help support, who are the people who are actually struggling, who are people at risk. And one of the things they turned to was unemployment data. It turns out governments don't really have a lot of unemployment data sitting around. They have sort of this unemployment insurance data. So for people who are not familiar, most of us are employees. We get this W-2 form. Part of that, our employers pay unemployment insurance to the state. And that sort of is a data set that they use to figure out who's unemployed. So what happened was a lot of examples like that where this data wasn't collected for that purpose, but government started using it to make decisions around support programs, assuming that represents ground truth on who is unemployed. Of course, most people employed are not, or a lot of people employed are not W-2 employees, they're not in the formal job sector, and that led to a lot of equity issues that came up when they made those decisions. And so that's really more of a teaser. There's a lot of policy work we were doing that was looking at, yes, we know that data is never sampled randomly, that it has biases and issues. What we were looking at was some of those data sources, when used as a proxy for ground truth, what was the equity impact of that? So in that case, a lot of people who are not formally employed are, typically, Black people, brown people, people, again, lower income, more unstable jobs, and they got affected. Another data source was shutdown decisions were being made based on positivity rate. Everybody knew that the actual positivity rate was nothing to do really with the actual prevalence, but yet that's what was available because they didn't know who actually had COVID. They knew who was testing positive. We all know the biases in that data. Yet when they were shutting down counties and different neighborhoods, they were using that data as a proxy, again, disproportionately impacting poor people, Black and brown people. Another data source was mobility data. I don't know how many of you use something like SafeGraph, same issue. So some counties were using that data to figure out compliance with shutdown orders. And again, we know that a lot of studies were done, found that that data was biased. Again, the usual, it was disproportionately missing typically older African-American people. And so now imagine the places that they were thinking, nobody's going there. That means that store must be shut. Well, there's a good chance older Black people are going to that place. So you're not checking for compliance. You're assuming that place is closed when it was actually open. And you're doing more compliance in places where younger, whiter people were going to. So we kind of went through a lot of analysis, interviews to kind of figure out some of these policy implications on COVID. So I'm not going to go into that too much. If you're interested, come talk to me afterwards. Happy to sort of talk more. What I actually, redundant slides. What I want to talk through is what happened, kind of one level beyond that is organizations trying to use machine learning to allocate a lot of resources to mitigate some of those issues. And sort of the common themes around those systems they were trying to build were, again, as we've talked about, sort of human machine learning collaborative systems. Right? They're not autonomous systems, they're supporting people. They're often in a limited resource scenario where we only have resources to provide support to X% of the people at risk, whether that's people who need mental health services, who need preventative health services, who need social services, benefit programs. And we're trying to juggle a lot of different policy goals. We might care about efficiency, which is trying to help as many people as possible with those limited resources, or effectiveness, trying to prevent things for as many people, or equity, which arguably should be the key goal. So what I want to sort of talk about is when we are making those decisions, we're often building kind of the standard ML models to predict who is at risk. And those risk models, we're familiar with. And what we do with those models is we generate that model, we generate a list of people who are at risk, we sort them with some sort of order of highest risk to lowest risk, and then we pick the top number based on the resources we have. And so let's say we had resources to test, 3,000 people in a given community, even let's say, for example, of COVID or other types of diseases. We would predict who's at risk, we would sort them, and then we would kind of pick the top 3,000 to allocate those resources to either provide support or to test. Now the question is, how do we pick those? We're picking them as highest risk, but that's thinking about the problem in terms of efficiency. Because that's just saying, if I intervene on 3,000 people, I want to maximize the people who are actually at risk. And that's the standard metric we use in machine learning. That's precision, it's variations of all sorts of kind of macro metrics. If that's what we cared about, if efficiency was our policy goal, that metric makes a ton of sense. If we had 3,000 things and we wanted to give them to people who needed them and maximize that number, that's great. But what if those people happen to be living in the middle of urban centers or were closest to pharmacies, all the things that we encountered, right? That would be efficient, but pretty horribly inequitable. And so when we're building kind of these types of machine learning systems, our standard metrics don't work. So the question is, how do we design these systems such that they help us achieve equity instead of just focusing on efficiency? And so, in terms of kind of making that equity metric, there's been a lot of work over the last 3 to 5 years on thinking about how do we make machine learning models think about or to be designed for fairness. And because we have a lot of math available to us, we come up with a bunch of metrics. And this is not even a whole list. Take a confusion matrix, take all the metrics you can possibly create, and there is a metric you want to equalize to get to fairness. Now, one result of all of these definitions of metric came around and says, well, what does it actually mean? Well, it means if we want to allocate equal resources to every protected group, we should care about this metric. If we want to allocate resources proportional to need, we care about this metric. If we don't want to miss people disproportionately who need some support of a specific type, we care about this metric. If we don't want to disproportionately intervene incorrectly on a particular group, we care about this metric. And so it makes a lot of sense systematically, but from the policy side of it, it really handicaps a lot of practitioners because they're not quite sure. Do I try to get all of them? Do I get one of them? And then papers start coming out that say, well, if you get this, you can't get that. And while that's true, one of the things we realized was that, well, you don't want to have all of them. They all have different contextual needs for when you care about one or the other. So one of the things we developed was what we call a fairness tree, which I'm not going to go into detail, but I'm going to zoom into a specific piece, which is thinking about what these machine learning models to do in terms of fairness depends on what you're doing with this model. If you're using it to support interventions that are trying to help people, so let's take, again, providing preventative health services. It's kind of this assistive, we're trying to help people, which means that missing people disproportionately is much worse for them than intervening if you don't need if you're not going to get a disease and I sort of test you. It's most, depending on the test again, if it's not something harmful, it's not as much big of a deal as missing you, right? So false negatives in this case matter a lot more than false positives. Vice versa, if I'm trying to preemptively denying you bail, all sorts of horrible predictive policing type things, a disproportionate false positive is much, much, much worse for you. In many applications, actually, it's kind of somewhere, it's unclear. And that we sort of, what this is supposed to do is not sort of give you a definitive A or B, it gives you sort of a prioritized order that comes from different types of people. And so in this case, a lot of the projects we've worked on over the last few years really involve things like working with criminal justice programs to figure out who might have mental health needs that are unmet, that we can prioritize them for proactive mental health services, or working with health departments to preemptively do inspections of different types to prevent, again, adverse incidents from happening, or working with school districts to help figure out which students might need extra support in order to graduate on time. And all of these kind of fall into this assistive setting, where you want to help people. You can only help, unfortunately, a small number of people. So we want to sort of equalize the false negatives that we have, which kind of gets to this equal recall or true positive rate. So when we try to kind of go into the setting, what it turns out is we sort of test a bunch of different, we kind of did this study where we looked at different methods for mitigating the bias. So when we build our initial machine learning models, they all end up being not fair. And that's not surprising because they're kind of maximizing this macro metric. They're trying to get as many things correct as possible, ignoring, we never told this method to be fair, so why should it be fair? So when we sort of take a lot of existing methods that have been proposed to try to correct for that bias, interesting things happen. So we kind of took 3 classes of methods. The first class was really things that we call pre-processing, which is things you do to the data before you build models to see if I can adjust my data, maybe the models will learn something more fair. It's kind of hoping that if I modify the data, the models will do something. The second is, what if I tell the model explicitly to care about fairness? And that's sort of these in-processing algorithms. And then there's a third class, which is, once I've built the models, can I adjust the output? Can I adjust the list that they're producing to make it fair? And we thought, let's compare all of these across a lot of projects that we'd worked on. And so here's what came out based on that. The first thing was we kind of the pre-processing, which is there's no reason to believe it should work, yet people do this all the time. They think, oh, I'm not going to use race in my model, so that should fix the model. Why would it? Race is correlated with everything else that we have in their data, unfortunately. But we wanted to have it there just to make sure that we put it there. So what happens is the blue is the original accuracy maximizing model. And so the way to read these graphs is, as you go to on the x-axis, that's kind of the accuracy. Y-axis is the disparity. So you want the ideal disparity to be 1, and you want things to be as far there as possible. So we notice that in different projects, the blue is sort of the original one, unfair, and maximizing accuracy, unfair, unfair, unfair. Orange is when you remove the race or the gender or the protected attribute. Doesn't do much. Sometimes it helps, sometimes it hurts the accuracy, sometimes it makes it worse. It's just, why would you do this? Yet people do this all the time. The second thing we did was people claimed, well, your model is biased because of distribution of the data. You have a small number of people, of women in there, a small number of black people, small number of brown people. So let's sample the data. Let's change the distribution. And that might tell the model to fix itself. So blue is original, and the greens are different ways of sampling. We tried all sorts of undersampling, oversampling, all the gymnastics people play. And again, the results are, not much happens. Because sometimes it goes up, sometimes it goes down, so it's not predictably doing anything. In some cases, we sort of see still, if the bias gets better, the accuracy gets worse. So then we went into these pre-processing. I'm going to just show you one of the pre-processing ones, which is, the way it works is, the typical machine learning methods will sort of have this function of how, regularization happening, which basically says, try to match this data, but, try to not to overfit too much. And so this adds this penalty term for bias as well. If you're biased, I'm going to give you an extra penalty. So let's fix that. Turns out, again, doesn't do anything. And so blue is kind of your original model, and the brown is the fixed model. Yep, it helps here, but reduces the bias a little bit, but hurts accuracy. Increase accuracy a little bit, but hurts your bias, reduces, but it's sort of, again, totally unpredictable. Shocking part is nobody's ever, these methods have never been tested, except people have been kind of talking about them for a long time. The last one we tested, not one of them, is we just said, what about we just use computers to build a ton of models? Let's just build all sorts of models, hyperparameters, just do us, and then use trust model selection to kind of find the best unbiased model. And this is where you start seeing a pattern, right? There's sort of this Pareto curve happening, where yes, you can reduce bias, but it hurts your accuracy. And that's kind of the assumption that people have made for a long time is, well, there's this trade-off. So then we said, well, okay, we've built the model. Let's now adjust the ranking of this model to see, can we get to fairness? And it turns out, and every single case, we don't reduce accuracy, get to fairness. Don't reduce accuracy, get to fairness. Number 3, number 4. That was shocking to us because we didn't expect this sort of very simple way of correcting. You generate the model, you separate the different groups, and then you kind of select the number of people from each group such that you maximize your accuracy under the constraint that you want to have this parity, recall, equaled as much as possible. And we find in all of these 4 cases that we end up getting absolutely no trade-off. We get the accuracy we have, and we get to the fairness. And I'll sort of, I don't have enough time to, well, I'll give you the intuition. So what we're sort of finding is that, basically here's that in all of these different cases, we can get from the original efficiency-focused models, the U, unadjusted models, to the fair models without losing accuracy. But we can't do that if we just pick up a random method that's sitting out there and use it, because this is what happens if you use these random methods. This very specific approach of kind of adjusting at the end seems to be, and I'm showing you 4 examples here. We've actually done it in several other cases, and we've found repeatedly the same thing here. The very quick, intuitive explanation why this works so well is in all of these problems, what we've got is we've got a lot of people who need support, that the model can predict their high risk, yet we can only help so many of them. So if you sort of think there are 1,000 people in this data, in this set, in this population who need help, where we can only help 300 of them, well, the 1,000 choose 300 ways of picking them. The efficiency-focused model picks one ad hoc set out of those that happens to be biased. If we explicitly asked it to pick one that we care about, that we wanted to balance different groups, there typically exists such group. We just have to deliberately design the system to ask for that. Once we ask for it, we find that it exists. So that's kind of the intuitive idea. We're still investigating that further to see how well that matches our what we're actually finding. So that's kind of the summary. Basically, I think was we in a lot of policy areas, machine learning is starting to get used. So far, it's been traditionally used to really focus on designing more efficient public policies or more effective public policies. And what we're sort of really focused on over the last few years is working with organizations to design them to be equitable instead of just efficiency. That means changing the evaluation, changing the metric that we're designing them, changing the goal. And then not sort of starting with, this, when we talk about these things to government agencies, they sort of say, oh, I read this paper that says you can't have both. We can't be not efficient. That's just not. And so it's kind of important that we don't, talk about that trade-off and actually focus on the empirical nature of this stuff, which shows that that trade-off doesn't exist in a lot of places. So it's possible to get both. And yeah, so those are kind of some examples of that. And yeah, thanks very much, and happy to chat afterwards as well.